Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
we live in a world of molecules interacting with other molecules in chemical reactions. What makes the reactions occur? Why are some fast and some slow? The rate of a reaction turns out to be critical, whether you're involved in construction, or winemaking, or simply preparing food. To understand these dynamics, we must probe the driving forces.
Chemistry is not just bottles on a shelf. That would be pretty dull. It's about chemical reactions, about compounds changing to make other compounds, about molecules bouncing around. It's a wonderful world of transformations. Take this apple tree. It grew from a seed, but on the way it used water from the soil, minerals and fertilizers from the soil also. It took in carbon dioxide from the air, and the sunlight provided it with the energy to do what? To run a chemical factory making a whole host of marvelous molecules, the chlorophyll in the leaves, the pigments in the skin of the apple, the sugars within, and it's still not static. Those leaves are going to change color. They are going to turn yellow. That's another chemical reaction. This whole tree will die someday. That's another set of chemical transformations.
Every change has a natural direction in which it occurs, whether in the wilderness or in the bustling world we've created. Rivers flow to the sea, never the reverse. In a complex series of chemical reactions, a flower blooms, then shrivels and dies, never the reverse. Wood burns, producing carbon dioxide and water. An automobile burns gasoline to carbon dioxide and water, and also produces heat and power for motion. In a vast chemical plant, an array of chemical reactions takes place. Here, for instance, ethylene reacts with water to make ethyl alcohol. Why do all these changes go the way they go? What determines the natural direction of a chemical reaction? When wood burns, the energy of the system decreases and heat is released to the surroundings. This tendency to reach a lower energy is one of the forces that drives all chemical reactions. In the natural direction of most chemical reactions, the energy of the system decreases. Dr. Donald Showalter.
In this reaction, the reacting materials are potassium permanganate, this dark purple solid on this screen, and glycerin, this thick liquid. Now let's see what happens when we mix them. I'll put the glycerin onto the permanganate. Oh, there's some smoke coming off. Oh, look at the flame. Well, that reaction certainly releases energy, doesn't it? Now, what happened is that glycerin is a combustible organic liquid, and potassium permanganate is a concentrated source of oxygen. So when the two come in contact, they ignite spontaneously. So this kind of chemical reaction releases energy. The key word is release. This is the type of reaction we call exothermic.
In an exothermic reaction, the reactants have relatively high energy. The energy is depicted here in kilojoules. The products of the reaction have a lower energy. As the reaction proceeds downhill from high energy to low energy, reactants are converted to products, and energy is released by the system, in this case, 300 kilojoules per mole reactant. As we have seen, most chemical reactions tend to release energy, usually in the form of heat. An automobile is designed to release energy in the form of motion down the highway and the heat from the engine. What about reactions in which heat is absorbed?
This time I want to do a reaction that takes in energy. Now, how are we going to see that? Well, let's do the reaction and find out. I'm going to mix barium hydroxide, a white solid, with another white solid, ammonium thiocyanate. And before I mix them, I'm going to put a little water onto this board. I'm going to move that water over here. Put the beaker onto the board, right on top of that water. Then I'll put the solids in there, and we'll see what happens. Here's the barium hydroxide, and here's the ammonium thiocyanate. I'm going to mix it. Oh, it's getting moist in there. Getting liquid. And that's understandable because one of the products is water. You can also smell a little ammonia coming off of there. That's another product. Oh, the beaker's getting cold down at the bottom down. I'll keep stirring so that the reaction proceeds, and we'll see if we can tell whether or not energy is taken in. Whoa, look at this. The beaker is frozen to the board. This is an example of an endothermic chemical reaction, one that takes in energy. In this case, the energy is taken in from the surroundings. That's why the beaker got so cold that it was able to freeze that little bit of water that I put on that board. So the beaker is frozen very tightly to that board. Look at that.
In an endothermic reaction, the reactants have a relatively low energy. The products have a higher energy. As the reaction proceeds along the uphill slope from low energy to high energy, reactants are converted into products. In this process, energy is absorbed. In this example, 400 kilojoules per mole reactant. Many important chemical reactions take in energy. Plants and animals will not grow without an infusion of energy. Reactions involved in cooking food also require that energy be absorbed. But an energy change is not the whole story. There's a second driving force, a tendency towards increased disorder. The scientific name for this disorder is entropy.
Entropy, it's a fascinating subject. Let's see how it works. I got a couple of things to do that will show how entropy works as a driving force. Let's do this one first. This beaker has pure water in it. I'm going to add a few drops of dye to that. Now, I already know that the dye and the water will not react chemically. Look at that. The dye and the water are mixing slowly in there. Now, they're doing that by itself. I'm not helping it out at all. Well, let me speed it up, though, a little bit. Now, any mixture is in a greater state of disorder than it is in the original materials. Now, do you think we can get them back into their original containers? But that's just a TV trick. We know that's not the way it happens in the real world. But what does this show us? That going from a state of disorder to a state of greater order is not the natural direction for almost any process. Well, let's try something else. Here I have some lettuce and some tomatoes and some peppers. Get all those tomatoes in there. Mushrooms and cucumbers. You know what I'm going to do? I'm going to make a salad. I'm going to toss that salad up here. Whoa, it looks pretty good, huh? Say in here. Looks pretty good to eat. If I kept tossing this now, will the salad go back to its original unmixed state? Well, you know the answer just as well as I do. Like the dye in the water, the salad shows us that the natural direction of change is toward greater and greater disorder, more entropy, increased entropy. Now, this is true for virtually any chemical reaction.
In what ways can entropy increase in a chemical reaction? There is more disorder or greater entropy if more molecules are formed. There is greater entropy if a liquid is formed from solids or if a gas is formed from liquids or solids. And entropy rises if a mixture is formed or if the volume of a gas is increased. Look again at the reaction that made the beaker freeze to the board. Why did this reaction occur? Energy was absorbed and the entropy increased. A liquid mixture with more disorder was formed in the beaker from two crystalline solids. The increase in entropy was large enough to overcome the absorption of heat. This must be true for all endothermic reactions. In industry, reactions have to work. Both energy and entropy effects determine that. If a reaction does work, if new molecules can be created, then the industrial design is given to the engineers, and they focus on energy and materials. West Virginia, Union Carbide, chemicals for 500 different products, detergents, adhesives, plastic wraps and car seats, paints and waxes. Probe the panoply of pipes and towers and you find more than a flow of materials. There's a flow of energy. Energy. Amidst scores of chemical reactions, the engineers must conserve it. Usually, a reaction is exothermic, giving off heat. Plant designers want to reuse this heat to drive other reactions, to minimize waste of energy in the whole plant. So through the red pipes in the scale model, they'll transport steam. And out in the plant, steam is piped from point to point, reaction to reaction. Materials. The basic raw materials coming into the plant are coal or petroleum, both high in energy. First, ethane gas is produced, and then, by selective addition of oxygen to ethane, we get a variety of industrial chemicals. The plant is constructed so that each product in the chain of reactions has a successively lower level of energy. Ethane is at the top of the energy ladder. From this ethyl alcohol is produced. Below that is ethylene glycol, used in antifreeze and adhesives. A further step down the ladder produces acetic acid for polymers like vinyls and rayon. And at the bottom of the energy ladder are carbon dioxide and water.
So whether a reaction will go or not depends on the balance of energy and entropy of the reactants and the products. And we can trade off one of these against the other. For instance, human beings like to have ordered things around them. We like to build. Can we construct such a local ordering, a local defeat of entropy in our environment? Yes, we can, if we put in energy. That is what is going on in this construction site in back of me. Energy and entropy tell us whether a reaction will go, but not actually how quickly it does go. For instance, concrete is being set in that building. It's important that it's set in hours, and not in seconds, and not in days. Let's look at the rates of chemical reactions and how we can influence them.
Roads, dams, bridges, churches, houses, and offices. There's chemistry in all that concrete. Trucked in slowly turning drums, the mixture of water and cement and gravel cannot set into concrete until it's spread on site. Boxed in place, it will be left to react slowly, water and cement reacting to produce microscopic bridges of calcium silicate with the gravel. If wooden forms are not left in place long enough, if not enough time is allowed for reaction completion, the consequences can be disastrous. In Virginia in 1973, the rubble remains of a partially collapsed apartment complex. 14 died. Too much haste for the slow reaction rate, which makes hard concrete. The rate of any chemical reaction depends on several factors. Don Showalter.
Let's take a look at one of the most common reactions of all, simple burning. Here I have a piece of wood. We all know that wood, if dry, will burn readily in air. And remember, air is about 21% oxygen. It's not burning. Oh, we've got to warm it up, don't we, to get it going. Let me warm it up with this match. Oh, I warm it up. The oxygen of the air reacts with the wood. There it starts going. Now that's burning pretty well, but not really well. I wonder if it'll burn any better in this 100% oxygen. Well, let's see. Oh, look at that. The rate of reaction is drastically increased. Now, what does this tell us? Well, there's a couple of things. The rate of the reaction is increased with increased temperature. Remember the match. And also, the rate of the reaction is increased with increased concentration of ingredients. Remember, 20% oxygen, 100% oxygen.
Temperature and concentration. Is there another general way of speeding reaction rate? There is, and it is employed in most reactions in the chemical industry. It involves using substances called catalysts.
Here I have a white powder, sodium potassium tartrate. It's about 30 grams. I want to dissolve that into this warm distilled water. This water is at about 70 degrees Celsius. Well, that's a fairly large molecule. I want to perform a chemical reaction for you where I break this big molecule down, degrade it. Now, the way I do that is by adding hydrogen peroxide, a fairly strengthy solution, 30% hydrogen peroxide. Now, if there is a reaction, you should be able to see carbon dioxide given off, bubbles. Let's see if it happens. I'll pour it in there. Whoop. Not many bubbles. Even though I heated it, and we know that heat increases the rate of a reaction, it didn't speed it up. So what else can we try? How about a catalyst? Let's add a catalyst. Now, I'll put it into this container just in case it does go pretty fast. Now, here's the catalyst. It's a solution of cobalt chloride. Let's add that to this reaction mixture and see what happens. Now, Now, a catalyst will speed up a chemical reaction, and look what's happening. The carbon dioxide bubbles are being given off. But one other stipulation for a catalyst is it must be the same at the end as it was at the beginning. Look at the rate of reaction. Notice it's green, so the catalyst is actually taking part in the reaction. Look at the steam being given off here. Oh, now if it's a true catalyst, what should happen? It should be the same at the end as it was at the beginning. Look at the color. It's back to that original pink color. What's a catalyst? It speeds up a chemical reaction, but it must be the same at the end of the reaction as it was at the beginning. It's pink again.
Special biological catalysts called enzymes are present in yeast, and that's important to the fermentation process in winemaking. It's one interest of food chemists like Dr. Theodore Labuza.
The production of wine from grapes is a fermentation process. In this case, we take grape juice, which contains sugars, and we add a yeast to it. In the ancient days, they didn't add yeast because they didn't know what yeast was, but there's naturally present yeast on the grape skins itself. And under the right temperature conditions, the yeast will ferment the sugars in there, produce alcohol, and the alcohol, in fact, prevents the growth of other microbes that would spoil it. If you didn't hold it on the right conditions, you would end up with something that was really god-awful. It would not be a good Cabernet Sauvignon.
Shipped around the world and across America. The rates of food spoilage, the rates of reaction, are vital knowledge for our global economy. A far-off country like New Zealand, for example, is almost wholly dependent on overseas markets for its lamb and butter and cheese. How do scientists study food spoilage and preservation?
The kinds of reactions that cause food to spoil are not very different than what chemists study in pure chemical solutions. What I always like to talk about food, it's the study of messy chemistry. And the reason I say that is that in a food which has so many different organic compounds and inorganic compounds together, there are lots and lots of different reactions that could cause spoilage. What we can do, however, is narrow them down to several classes. One, reactions that are enzyme catalyzed. For example, when you bite into an apple, you see it start to brown. That's an enzyme reaction. There's reactions that make it go rancid. Potato chips, for example, if they sit around for a long time, the fat goes rancid.
Modern techniques of food preparation and refrigeration have greatly reduced spoilage. Still, the shopper might like further proof that reactions have been retarded, that food is as fresh as possible.
One of the more interesting things that we're doing in our laboratory here, which is an application of chemical kinetics, is the study of little devices that can be used to monitor time temperature when a food goes through a distribution cycle. Now, why do you want to do that? Well, since foods deteriorate at a faster rate when the temperature goes higher and at a slower rate when the temperature goes lower, if you had a device that could be put on a package that would essentially integrate the time temperature exposure and show a color change that could be related to the loss of quality of the food, then by simply picking up a package and looking at a device that may be on the package, you could tell how much more shelf life is left, so you'd know when to consume it.
From supermarket to space. The manned space program has been an exciting challenge for the food chemist investigating rates of reaction. Dr. Labuza.
Why would one want a very long shelf life for space foods? These astronauts were only up there for a matter of days to maybe several weeks. Well, in fact, the foods had to be produced maybe 6 to 9 months ahead of time because we never knew when a rocket was going to go off. And so they had to have the foods in storage. And what we wanted to make sure was by the time the rocket went off, the food was still of good quality. And that's why we really had to study the rate at which the quality was lost and to package it in such a way that we could minimize that rate of quality loss.
To review, in any chemical reaction, substances are transformed into completely different substances. The natural direction of a chemical reaction is determined by the tendency to go in the direction of lower energy and higher entropy. In an exothermic reaction, energy is released. In an endothermic reaction, energy is absorbed. The speed of a chemical reaction is determined by the nature of the substances involved, as well as their concentration and temperature. A catalyst is a substance that increases the rate of a chemical reaction. Sometimes, as in the case of preserving food, it is necessary to slow down a chemical reaction.
You know, when I see that reaction that Don Showalter ran in a laboratory, when he mixed hydrogen peroxide with a solution of sodium potassium tartrate, and at first nothing happened, and then he added a catalyst, and there were color changes and bubbling. When I see that, a terrible urge overcomes me. I want to know what happens in there. I'm not satisfied with seeing the colors. I want to see what the molecules are doing. How can I do that? How can I find out something about those tiny things? Well, those colors can be looked at with a spectrometer. Those messages from within can be decoded. Oh, they happen quickly, those color changes, but I can try to move quickly. I can try to fight nature and slow down the reaction by cooling it. I can build a faster spectrometer. Slowly, laboriously, we can build up a picture of what happens in a chemical reaction, whether it's Don's experiment or in the leaves of that tree. The explanation must lie at the molecular level. This is what we'll see in the next program.
Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And